The solid state. As already discussed, the matter has three states, viz. Solids, liquids and gas. We have already discussed the gaseous state. This chapter highlights about the solid states of matter. Ice, water and steams are the three states of water. Property of solids. First, solids have definite shapes and volume. Second, solids have high rigidity. 3. These are non-compressible. Fourth, they have high mechanical strength. Fifth, ions, atoms or molecules in solids are closely packed. Sixth, they are held together by strong forces. Seventh, the particles in the solids have high potential energy and negligible, very small kinetic energy. 8. Solids are both hard and soft. Kind of solids: A. Crystalline solids, B. Amorphous solids, and C. Polycrystalline solids. First of all, we shall describe amorphous solids, then polycrystalline solids, and finally crystalline solids. Amorphous solids. This material do not have ordered arrangement of constituent particles. They are not crystalline. In fact, amorphous solids have a short range order in which there exists some ordered arrangement around a particular atom or ion which lasts up to short distance. Example of amorphous solids are glass, fused silica, rubber, pitch, etc. Amorphous solids possess following property. First, they do not have a sharp melting point. Second, they do not have definite ordered arrangement of atoms and molecules. Third, this substance possess compressibility and rigidity to some extent. Fourth, the potential energy is higher as compared to crystalline substance. Polycrystalline solids. Sometimes solids material exist in powdered form, resembling amorphous solids, but its individual particles has all the properties of crystalline solids. These solids appear to be isotropic while each single crystal is an isotropic. Classification of crystalline solids. On the basis of bonding, crystalline solids are grouped into four classes. A. Iron crystals, network of cations and anions. Example: sodium chloride, potassium chloride, sodium sulfate, etc. B. Covalent crystal, network of covalent atoms. Example: diamonds, quartz, sand, etc. C. Molecular crystals, simple molecules. Example: copper, silver, gold, zinc, iron, etc. Types of solids. Solids with different type of bonding are given in the table below. Solids. Nature of bonding type of solid. Carbon dioxide, van der Waals, molecular solids. Magnesium oxides, ionic bonding, ionic solids. Sodium, metallic bonding, metallic solids. Dinitrogen, van der Waals bonding, molecular solids. Diamonds, covalent bondings, network covalent solids. Zinc, metallic bonding, metallic solids. Ice, covalent bonding, dipole-dipole solids. Lead, metallic bondings, metallic solid. Silver chloride, strong electrostatic bonding, ionic solids. Crystal. It is a homogeneous substance made up of irregular patterns of structural units, ions, atoms, or molecules bonded by a plane surface, making definite angle with each other, giving a regular and definite geometric forms. Crystal lattice. Space lattice. Lattice is the regular pattern of points which describe the three-dimensional arrangement of particles, ions, atoms, or molecules in a crystal structure. Unit cell. On connecting lattice point series of parallelepiped are obtained. Each parallelepiped is the smallest, but it is a complete unit and is called unit cell. Repetition of unit cell in three dimensions gives out the crystals. Simple crystal lattice. A unit cell having lattice points only at the corner is called simple, primitive or basic unit cells, and it is known simple crystal lattice. Face-centered unit cells or FCC. In a FCC crystal, a unit cell have a constitutional particles at the corner as well as the center of each face. It is called face-centered unit cells. Body-centered unit cells or BCC. In a BCC crystals, a unit cell have lattice points at the center of the body in addition to the lattice point at the corner. It is called body-centered unit cells. Cubic cell. In a cubic crystal's density, rho, number of molecules per unit cubic, P cell, N, Avogadro's number, Na, molar mass of the substance M, H, length of a cubic cell A, and volume A raised to cube, can be calculated by the following formulae. 1. Rho equal to N upon A cubes in bracket M upon Na. 2. For a primitive cubic cell, R is equal to A upon 2. 3. For a body-centered cubic cell, R is equal to square root 3 upon 4A. 4th, for a face-centered cubic cell, R is equal to square root 2 upon 4A. Intersticts the particles in a crystals. Pack themselves is closets. When the particles arrange themselves so that their center are the corner of an equilateral triangle, since the particles touch each other at certain points, so there is some empty space or void between them. The void in a crystal is called interstices, tetrahedral void or holes. When a center of four particles in a crystal lie at the corner of a regular tetrahedrons, then empty space between this is called a holes or void. The shape of this vacant space is triangular. In HCP and CCP there are two tetrahedral voids. The size of these voids in comparison with a sphere size is 0.225. R void upon R sphere is equal to 0.225. Octahedral voids or holes. When a closed packed system is obtained by joining centers of six particles whose octahedral voids or holes. When a closed packed system is obtained by joining center of six particles whose centers lie at the corner of a regular octahedron, then the empty space between this is known as octahedral void or hole or site. This type of hole is a double triangle joined in such a way that a pair of these triangles are in opposite direction. In HCP and CCP, there is only one octahedral void associated with each other. The ratio of the size of the octahedral void and the size of the sphere is 0.414. R void upon R sphere is equal to 0.414. Coordination number. Number of particles surrounding a single particle in a crystal lattice is called its coordination number. The coordination number of both hexagonal and cubic close packed structure is 12. In a body center cubic unit, where the spheres are close packed, each sphere has a coordination number of 8, while in simple cubic cell the coordination number is 6, and in face center cell the coordination number is 12. Structure of sodium chloride NaCl. Its structure can be discussed as follows. Its structure is cubic close packed, that is face center cubic. 2. The sodium ions occupy the octahedral voids in the cubic close packed crystals of chloride ion. 3. There are 6 octahedral voids around each chloride ion. Therefore, each chloride ion is surrounded by 6 sodium ions. Similarly, each sodium ion is surrounded by 6 chloride ions. Thus, coordination number of each is 6 and is called 6:6 coordinations. Fourth, the radius ratio Rna plus upon Rcl minus should be equal to 0.414, but actually it is 0.525. Fifth, the unit cell of sodium chloride has 4 sodium and 4 chloride ions. Sixth, the number of NaCl unit per unit cell is 4. Sodium chloride structure is also known as rock salt structures. 7. Most of the halide of alkali metals and oxides of alkaline earth metal have this type of structure. The example is iron oxide. Structure of cesium chloride CaCl. 1. Cesium chloride, the chloride ions are at the corner of a cube, whereas cesium plus ion is at the center of the cube, or vice versa. 2. This crystals has 8:8 coordinations. That is, each ion is in contact with 8 opposite ions. 3. The radius ratio in cubic void RCS plus upon RCl minus should be equal to 0.732, but actually it is 0.93. Fourth, the unit cell of this crystal has 1 Cs plus and 1 Cl minus. Structure of zinc sulfides. This structure it is known as follow. First, in this structure, sulfide ions have cubic close packed or face center cubic lattice, and zinc ions occupy half the tetrahedral void. 2. Each sulfide ion is tetrahedral surrounded by 4 zinc 2 plus ions, and each zinc 2 plus surrounded by 4 sulfide ions. Thus, zinc sulfide has 4:4 coordination. 3. For exact fitting of zinc 2 plus ion in tetrahedral void in the close packing of S2 minus ions. The ratio Zn2 plus Rs2 minus should be 0.225. Actually, this ratio is 0.40. Fourth, the crystal has 4 zinc 2 plus ions and 4 S2 minus ion per unit cell. Fifth, some other example of ionic solids having zinc sulfide structures are copper chloride, copper bromide, copper iodide, silver iodide. Structure of calcium difluoride. This structure is known as follow. First, calcium 2 plus ions are arranged regularly in the cubic close packing. 2. The fluoride ion occupy all the tetrahedral void in the lattice of calcium 2 plus ion. 3. In CCP lattice, there are 2 tetrahedral voids per atom. It means that for every atom of calcium 2 plus, there are 2 tetrahedral sites, since fluoride minus ions occupy all the tetrahedral sites. Hence, for every calcium 2 plus ion, there will be 2 fluoride minus ion. So, the formula of calcium fluoride is calcium difluoride. Fourth, in the crystal, each fluoride ion is surrounded by 4 calcium 2 plus ion, while every calcium 2 plus ion is surrounded by 8 F minus ion. Therefore, the coordination number of calcium 2 plus ion and F minus ion is 8:4. Fifth, the structure of disodium oxide is similar to calcium difluoride, but the two structures differ with respect to position of cations and anion. In this case, oxygen 2 minus ions arranged in CCP and sodium plus ion occupy tetrahedral sites. In this structure, the coordination number of sodium plus and oxygen 2 minus ions are 4 and 8 respectively. This structure is called as anti-fluoride structure. Other examples of fluoride structures are strontium difluoride and cadmium difluoride. Radius ratio R. Radius ratio of R base to the R is equal to R plus upon R minus. Structural arrangement. Example, radius ratio, coordination number. Structure arrangement, cubic. Example, cesium chloride. Radius ratio 0.732 to 1. Coordination number is A. Octahedral structural arrangement. Example, sodium chloride. Radius ratio is 0.414 to 0.732. Coordination number is 6. Structural arrangement tetrahedral. Example, zinc sulfide. Radius ratio is 0.225 to 0.414. Coordination number is 4. Structural arrangement triangular. Example, boron oxide. Radius ratio is 0.155 to 0.225. Coordination number is 3. Stoichiometric lattice defect. In ionic crystals, there are two kinds of lattice defect. First, Schottky defect. Lattice points unoccupied. This kind of defect may arise between some of the lattice points are not occupied. This defect occurs in highly ionic crystals having high coordination number, and when positive and negative ions are of smaller size, it is more common. Example, sodium chloride, potassium chloride, cesium chloride and potassium bromide. 2. Frankel defect. Atom occupying position between the lattice points. This defect occurs due to big difference in the size of cation and anion. Due to small size of cation, they generally leave its place in the crystal lattice and occupy position between the lattice point. It is less common. Example, silver bromide, calcium difluoride, zinc sulfide, silver iodide. Non-stoichiometric defect. Compound having different positive ions or negative ions are called non-stoichiometric compounds. The balance of positive and negative charges is maintained, first by having extra electron, or 2 by having extra positive charge present. This defect are of two types: A. Metal excess defect, B. Metal deficiency defect. First, metal excess defect due to anion vacancies. Example, yellow color sodium chloride. 2. Metal excess defect due to interstitial cation. Example, zinc oxide. 3. Metal deficiency due to cation vacancies. Example, A. Nickel oxide NiO, B. Ferrous oxide FeO, C. Ferrous sulfide FeS. 4th, metal deficiency due to presence of interstitial anion. Piezoelectricity. The substance in which alignment produce a net dipole moment exhibit the phenomenon of piezoelectricity. When such a crystal is subjected to mechanical stress, there occurs some voltage across the phases. Thus, a piezoelectric crystals act as a mechanical electrical transducers. These crystals are widely used in record players, where they produce electric signals by the application of pressures.